Hi Rockridge, this is Mrs. Berger, and today we'll be going through the topic for Unit 1, Day 2, imaginary numbers, which we began to discuss on Day 1, and rationalizing a denominator that has an I in it. So just to get us started, what is this crazy thing we're talking about with this I? So let's really quick, just straight up define what I is. I is defined as the square root of -1. And why is that helpful? Miss Morgan has this great problem that we tried to do in Algebra 1 that's a great example of why we would need this. So she says if you ever came across x squared plus 1 equals 0 in algebra class, how would you solve for x? And she says, well, we all know that you subtract 1 from both sides. And then we say, well, at this point I would take the square root of both sides, but then square root of a negative, I can't do square root of a negative, right? We were told I can't do that. The reason we can't do that is because that's an imaginary number. The square root of -1 is an imaginary number. It is I, okay? And that is going to be very useful when we start looking at the roots of quadratics. So let's manipulate I. Let's see what we can do with these i's. The first thing we can do is if I is ever squared, if we ever have I squared, we should know that I squared can always be replaced with a -1, which is incredibly useful. We'll see that today. So just think about that. Instead of, let's pretend like we've got square root of 2. And we square it. Well, square root of 2 squared is 2. Same thing happened here. Square root of -1 squared is -1. Okay, so I squared being -1 is a property that we're going to use constantly. Just so you know, standard form of a complex number could have an imaginary part and a real part. The real part comes first, followed by the imaginary part. So that's standard form for a complex number. When we talk about pure imaginary, that just basically means the real part is a 0. So we just have the imaginary part for that number because the real part of the number was 0. Okay? So let's start looking at all the different powers of I. We started with the first power, I to the 2 power, and we saw what that did. But we could be bringing I to all kinds of different powers. And if you were ever to bring I to any power, the answers are always going to be one of 4 things. It's either going to be I, the answer is going to be 1, it's going to be -I, or -1. Okay? So those are the different things that we could see. If you would like to use this circle chart, it's certainly a great reference. If you ever have I to any power, so let's just say I to the 87th power, to the power of 87 for an example. This method for determining how to reduce or simplify this is to take 87 on your calculator, type 87 divided by 4, and you'll get, your calculator will spit out 21.75. Okay? And if you're somebody who likes using this chart, you will have memorized all the corresponding values. If 0.75 is what's left over, this remainder here, then that means that you reduce to -I. So that means I to the 87th power can be reduced to -I. Okay? So this is just one method to figure out the different values of I being brought to different powers. So again, you divide the exponent on the I, you divide the exponent by 4, locate the decimal value in the parentheses right here on the coordinate plane that you've memorized. You'll have to memorize this chart. And the power of I is simplified to that. Okay? And you can do this with many different examples, to try it out if you'd like to pause the video and see. Another method you can do is you can notice that the pattern of these powers repeats. So I to the 1 power is I to the 2 power, which we saw at the beginning, is -1. I to the 3 power, well, if you think of that, that's just I to the 1 power times I to the 2 power. So that's -1 times I, which is -I. I to the 4th power, well, we can think of that as I to the 2 power times I to the 2 power. So that's -1 times -1, so that's 1. So this pattern repeats itself. I, -1, -I, 1. Then we start the pattern over again. I to the 5th power, think of that as I to the 4th power times I to the 1st power, so that's I again. I to the 6th power, -1. I to the 7th power, I to the 8th power is 1, and it repeats itself over and over and over again. So you can think of this, if you have these higher numbers, you can think, okay, let's once again, let's find out how many times 4 goes into this, right? Because the pattern repeats itself after every 4 times. So 80, if I try again, I to the 87, 87 divided by 4, so we can see how many times it wraps around this pattern. 87 divided by 4, that's 2, minus 8, 0, bring down the 7. 4 goes into 7 one time. We subtract the 4 and we have a remainder of 3. So this remainder tells you, okay, I wrap around this pattern of 1, 2, 3, 4, and I go around it 21 times. And then after the 21st time I came here, I had a remainder of 3. So a remainder of 3 means I go 1, 2, 3. Negative I is what that simplifies down to. I to the 87 is negative I. That's definitely my favorite. I'm not a big circle memorizer person. I memorize this pattern, and then I just figure out what the remainder is of the division by 4. Okay. I know this is going a little fast, so please pause the video and repeat or stare at the chart for a little while to see how you feel about it. Now, if you have your TI calculator handy, you can also take a look at this on the calculator. The function, the imaginary I, is found by hitting the second period button, or decimal. So that's how you bring up I. And then if you need to bring I to any particular power, let's try 87 again. If you want to try to bring I to the 87th power, bring that I up, do your little caret up here to get your exponent, and then put 87 in. So this is asking the calculator, hey, what's I to the 87th power? And we hit enter. Now, depending on what model calculator you have, you may have nasty looking output like this, or you may have nice clean input. So if you have one of the newer, skinnier calculators, they often will tell you that the answer to this is negative I. If you'll see right here, that's where that is right there. See, that had negative I. But you might be asking, those of us with the thicker calculators or the older ones or this emulator software, what is all this junk right here? Well, you need to interpret this for what it is. This is 3.7 times 10 to the negative 12. Remember scientific notation from science class? So what this means is, remember what times, the E means times 10, so times 10 to the negative 12 power. Well, what's negative 12 power? Remember that? That's moving this decimal to the left 12 times. So this is telling you that it's 0.0000000037, which is essentially 0. So this is 0 minus I. Remember our standard form? So this calculator is telling you this is essentially 0 minus I, or negative I, which is, of course, what we came up with here of I to the 87. We did that both ways, okay? So on the calculator, you've got second, and then the period. That'll get you your I, and then you'll do your caret 87. And then you'll just need to interpret the results if you don't have one of the skinnier calculators, okay? It takes some getting used to, definitely practice. Let's do some, speaking of, let's do some practice right here, okay? So let's simplify these. So I to the 2 power, well, that's the same thing as square root of negative 1 times square root of negative 1, right? So you can either remember that fact and say, oh, I know that's negative 1. You can run through and memorize that repeating pattern of 4, or you can divide 2 divided by 5, which is 0.5, and then go back and look at where 0.5 lands on your calculator, so negative 1. Okay. So that's one of the simpler ones. I to the 8th. I am definitely the pattern user, so I like memorizing that this goes this way over and over again. So I would say that this is 1, so this is I to the 1, I to the 2, I to the 3, I to the 4, 5, 6, 7, 8. If you divide 8 by 4, you will, of course, get something that's a whole number. And when you get that whole number, you know that that simplifies down to the 1. So these are your answers. If you look at number 3 here, I to the 11th, the way I would do it, I would say I would go here to 4, 8, 9, 10, 11. So that's negative I. Or pause and use the method that you prefer to use. I to the 46. Divide the 46 by 4. The closest I can get is 44, so I'll go around here. This will be 44, 45, 46. So that reduces down to negative 1. And these are your answers. So when we ask you to simplify or evaluate these, we're going to want you to tell us the answer is negative 1, 1, negative I, -1, okay? Your answer to all of these is going to be one of these 4 values. It's never going to be anything else, okay? Now let's ramp up the difficulty a little bit. Not only do we have these powers of I, but we also have things being multiplied by them. So this is basically saying take 5 times I to the power of 101. So 5 times I to the 101. So I know that 4 goes into 100 nice and cleanly. So if I go around this 25 times, I'll end up here at 100. And then 101 will give me positive I. So I'm going to replace I to the 101 with I. Minus 6 times whatever I to the 15 reduces down to. Well, I know 15 divided by 4 gets me down to 12, 13, 14, 15. So negative I. And again, if you are take the 15 divided by 4 on the calculator and look at what the decimal remainder is and match it up on the chart, that's totally fine. The one we just did here, 15 divided by 4, would have given you a 0.75 when you divide it on the calculator. So you'll be replacing that with a negative I, just like I did. Okay. Now, do you think we can leave this way? Absolutely not. We need to simplify just a little bit further. So 5 times I, obviously that's 5I. Negative 6 times negative I turns into 6I. And as we'll see in just a second, when you've got these combinations of i's, they act just like x's did in algebra class. Okay, they act just like any other variable, even though they're special. This reduces down to a total of 11I. Okay, they act just like any other variable you've seen. It's just they're a special one that reduces down to the square root of -1. So that would be the answer that you would circle. Okay. So let's continue to manipulate these. We did a little bit of that here in question number 5, but let's keep going. We're going to add, subtract, and multiply complex and imaginary numbers. Again, we're just going to treat I like any other variable. Okay. So if this was an x instead of an I, what would we do? We've got a number plus a number. There's an invisible 1 out here. So we're going to take 8 minus I plus 5 plus 4I, and we're going to combine like terms, just like we did with x's. So I'm going to combine the 8 and the 5 and make it a 13. And I'm going to combine the negative 1I, and 4I, and make that plus 3I. Okay? Now we just use distribution property just like we do with every other variable. So we distribute this 3, make it 15 minus 12I. And there are no like terms to combine, so that's your final. We've got a little extra work here to do. We need to distribute this 4 here and this -6 here, and then we'll combine like terms. So let's run through those steps. That's 12 minus 8I minus 48 minus 6I. I've got some like terms to combine. I will take my real numbers, the 12 and the -48, and put those first for standard form. And then I'll take my -8I and my -6I and combine them to make -14I as the imaginary part of this complex number answer. A little bit more distribution here. Now watch what happens here. I'm going to distribute 6I to 3 and make that 18I. And I'm going to distribute 6I to 3I, and watch what happens. 6 times 3 is 18. I times I is I squared. What did we say we could always replace I squared with? -1. Every time you see this I squared, you need to remember, from back up here, you need to remember I squared can always be replaced with -1, and you always need to do that. Your answer will not be completely simplified if you don't do this step of replacing this with a -1. So let's watch what happens with that. We've got the 18I plus 18. Now it's 18 times -1. What does that turn that into? It turns it into a -18. So your final on this is -18 plus 18I for your standard form. Okay. If you were to leave this answer as 18I plus 18I squared, you would not have a complete answer. That is not completely simplified. Okay, so always replace every single I squared with a -1 and multiply that out. All right, number 11, remember FOIL? Let's go back to our days of foiling. So first times first, whenever you have a binomial times a binomial, You use first times first, outer times outer, inner times inner, and last times last. Okay, so let's do first times first. That's your F. Outer times outer, negative 8i is your O. Inner times inner, that's plus 15i, that's your I. And last times last, that's negative 20i squared, that's your L. So remember FOIL. Now once again, we need to combine like terms, and we also need to make sure that we replace this pesky little I squared with a negative 1. So let me do a little bit of work here. This 6 doesn't have any buddies yet, but these I terms do. So let's combine these buddies, negative 8i and plus 15i. Let's make that a 7i. Combine that all down. Now this negative 20, remember what we replace I squared with? With a negative 1. Be careful. When you replace this with a negative 1, it's multiplying negative 1 times negative 20 to make it a positive 20. A common mistake folks do is they write negative 1 here, and then they forget, oh, I got to multiply that. We're not taking negative 20 minus 1. We're multiplying negative 20 times negative 1. Okay, so make sure you don't make that mistake. One little last step of combination, right? That 6 all of a sudden has a buddy now, which is the whole point of doing this. This I squared serves a function, and this is it. This is what it's all for. Making this a nice pretty 20 that can be combined with the 6. And then, of course, that 7i has no other friends. He just stays there. Okay, so that's your complex number. Let's do FOIL again. First times first, outer times outer. Inner times inner. And last times last. Let's combine what we can here in this first step. Let's replace this with the negative 1 to make this plus 14. And then let's do our last little combo of these terms here. Negative 22 plus 71i. Okay, and again, if I'm going too fast, please pause the video. Try it yourself, play the video back, make sure that you're good on these steps, because we're going to be doing this on the quiz and the test. All right, a couple more. Common mistake here when we see this, we forget that this means that we're distributing a negative 1 first and then combining like terms. So let's distribute this here. This negative 1 here makes that a negative 6 minus 7i, and then plus the 4i. So make sure you do that first before you combine like terms. And of course, after combining like terms, this is our final. Once again, we have a distribution situation, so we'll distribute this to make negative 24i plus 4i squared. We may not leave it like this. Why is that? Because this I squared must be replaced with a negative 1. So 4 times negative 1 is negative 4 minus 24i. That's your final on that. Now this is a fun problem that's going to lead us into our conversation about conjugates. So let's watch what happens here. Once again, we've got a binomial times a binomial, so we must use FOIL. First times first, outer times outer, inner times inner, and last times last. Watch what happens. Negative 12i and positive 12i cancel each other out, just like they do with any other variable. So those cancel each other out. I'm left with 9, and then don't forget, this I squared must be replaced with its alternate ego, which is negative 1. So negative 1 times negative 16 turns it into a positive 16, to simplify down to 25. See how pretty this is? There's no I component to this number. There's no imaginary component to this number. This is a very useful tool that we'll watch happen here in the next couple minutes. A very, very useful tool. Notice the properties of this binomial compared to this binomial. And we'll look at the outcome. So what you just saw was an example of using conjugates. So did you see what happened in number 15 above? When we multiply or simplify, here's another version, 2 plus I times 2 minus I, just like we just did 3 plus 4i times 3 minus 4i. Watch what happens again. We'll do first times first, outer times outer, inner times inner, and last times last. And once again, these imaginary components cancel one another out. This gets replaced with -1, so we have a -1, or a +1, and it comes down to a nice, pretty, real number. Conjugates are what we just used. So 3 plus 4i is the conjugate for 3 minus 4i, and vice versa. 2 plus I is the conjugate of 2 minus I, and vice versa. So conjugates are the same binomial with the opposite sign on the second term. Okay, you only change the sign on the second term. You do not change the sign on the first one. See how it's the exact same number on the first term? The second one is the only one that gets the sign changed. And when you do that, you've just created the conjugate. Okay, and as you see, these are very useful things. If you take a number and multiply it by its conjugate, you get a beautiful outcome here. Nothing with these messy little imaginary components. Okay. We're going to use these conjugates to rationalize a denominator. Well, what the heck does that mean? Rationalizing the denominator means converting the denominator into a rational number. And we'll see that. See these, let's do these together. See how this is a complex number. This is a pure imaginary. This is a complex number. That is not proper form to leave our final answer like that. So if you did some work down the road when we get into quadratics, if you end up with this as your answer and you're looking at those multiple choice answers and you're just like, I just don't see that answer, it's because you have not yet rationalized your denominator. Okay? Why do we do it? One reason is to show that you can show equivalent expressions and that you can recognize that, yes, I did in fact get the right answer. Maybe I got down to this simplification. I just need to put it in a different form for proper form. Okay? So let's stop talking, in words, and let's get back to numbers. Let's do the work on simplifying these rationalizing the denominator. Like I said, we don't like this form because it's a complex number down here with an imaginary component in the bottom. That's not allowed. The way we take care of this is we use the magic of that conjugate we just saw at work. What's the conjugate of 1 minus 2i, this pesky denominator? Conjugate of that is 1 plus 2i. Okay, we're going to make use of that by multiplying that bottom by its conjugate. We're going to get a nice pretty number like we did before. Now, the only problem is I'm not allowed to just random willy-nilly just multiply by this conjugate. In order to not change the chemical makeup of this number, I have to multiply by some version of 1, right? By multiplying by 1, I don't change anything about it. So I have to do this 1 plus 2i to the bottom and the top. Okay, by doing this, I'm just converting this number into a different form. I'm not actually changing that number into something that it's not. Okay? So whatever you do to the bottom to fix the denominator, you must do to the top. So let's see what happens when we do this. On the top, we just distribute a 1 into here, and we just get 1 plus 2i on the top. And that's fine. We don't mind these crazy things on the numerators. We just don't like them on the denominators. That's not proper form. Now let's FOIL out the bottom that we've done for ourselves here. So that's first times first, outer times outer, inner times inner, last times last. The middle cancels as we hoped it would. That was the whole point. Our top really doesn't change. 1 stays. -4 times -1. That turns into a +4. So +4 plus 1 is 5. That now, see that gorgeous denominator? It's no longer this problem denominator. We're happy with this answer, and this is the answer you'll find in your multiple choice options. Okay, you're not going to find 1 over 1 minus 2i in your multiple choice options. Let's switch colors because we're kind of getting close here. So this other guy is also a problem. There's an I component. The only difference is we don't have a complete complex number. We just have a pure imaginary down there. There are a couple of ways you can fix this. The simplest way is to multiply by I over I. Watch what happens. Again, we've got a version of 1 here, so we're not changing the chemical makeup of this. We're just multiplying it by 1. The top becomes negative I. The bottom becomes 4i squared. What do we always replace I squared with? We replace it with negative 1. So this turns into negative I over negative 4. Always, never leave a negative and a negative here. So negative divided by negative, that's a positive. So we'll change that into I over 4. Okay. Now, sometimes kids forget, because they're so wrapped up in this whole changing the sign thing, they forget that they could just use this simple I over I. And they think, well, aren't I supposed to multiply this by negative 4i over negative 4i? That's certainly an option. If you want to do that, it'll work out just fine. It's a little more simplification work. So let me copy that problem here. So the original problem is negative 1 over 4i. If you decide that you want to do a negative 4i over negative 4i to take care of this, this will still work, okay? I guess you could call this the conjugate. That's fine. The complex conjugate of this to take care of it. It's a little bit more work, but it will still work. It'll still get rid of that pesky I on the bottom. Watch what happens. Negative 1 times negative 4 is positive 4i on the top. And then here we turn this into negative 16i squared on the bottom. What do we always replace I squared with? Negative 1. Negative 1 times negative 16 is positive 16. And we still had a 4i. But wait, we have one more step of simplifying. 4 and 16 reduces down to 1 over 4. So check it out. Those are the same answers, okay? So there are a couple of different ways that you can get rid of these pure imaginaries on the bottom. The most basic way of dealing with a pure imaginary on the bottom is multiplying it by I over I. If you forget about that and you're so wrapped up in the whole complex conjugate to take care of this problem, that's fine. It'll still work out. Do not leave me with the 4i over 16 as your answer, though. You need to keep going down, because the kids who did this version got I over 4. You also need to be getting I over 4 as your final most simplified answer, okay? Because the name of the game here is simplify completely, okay? All right, let's do one more of the complex on the bottom. Give me a second to think about what the conjugate is of this. Think about it for a second. What do you think it is? You should have thought of 4 plus 5i. Only change the sign on the second term. Whatever happens to the bottom must happen to the top. Okay. Let's take care of multiplying this out. So I will distribute this in. So 12i plus 15i squared over first times first, outer times outer, inner times inner, last times last. Now, we have a couple things we need to take care of here. This cancels. Check it out. We've got an I squared in 2 places. We need to take care of both of them. Everywhere you ever have an I squared, you must replace them with negative 1, okay? So this turns into a negative 1 times 15. So I've got a negative 15 plus 12i on the top. And on the bottom, this I squared turns into a negative 1. Negative 1 times negative 25 is positive 25. 25 plus 16 gives me 41. Which is a nice, gorgeous little number on the bottom that has nothing with i's in it, so I'm happy. Again, i's on top is fine, as long as they're not I squareds, right? I's on top is fine, no i's on the bottom, that's bad form. Okay. So go ahead and try the remaining practice together and check with your teacher. Make sure that you understand all these concepts, and then you'll have some independent practice to work on as well.